Hello everyone, myself Dr. Ashish Prakash. I am in ABES Engineering College, Ghaziabad. Today we will discuss Gauss Divergence Theorem. First of all, we will learn what is this theorem. This is the statement of Gauss Divergence Theorem. Gauss Divergence Theorem is basically the relation between surface and volume integrals. And its statement is if f is a vector point function having continuous first order partial derivatives in the region V bounded by a closed surface S, then double integral f dot n ds under the surface S will be equals to triple integral divergence of f dv under the region V, where n cap is the outward drawn unit normal vector to the surface S. Correct. So this is the statement of Gauss divergence theorem, and now we will discuss this theorem by some questions. So first of all, very first question is find the double integral of f dot n ds where f is defined by f equals to 2x plus 3z I minus I cap minus xz plus y z cap plus y square plus 2z k cap, and S is the surface of the sphere having center 3 comma minus 1 comma 2 and its radius is 3. Correct. So let us solve this problem. So let V be the volume of this enclosed surface S. Then by using Gauss divergence theorem, double integral of vector f dot n cap ds will be equals to triple integral of divergence of f dv. Let us put the results given in the numerical. We have given the value of f. Let us put this result. Triple integral divergence is denoted by del dot f dv under v. Here del is defined by I del upon del x plus j del upon del y plus k del upon del z, where I, j, k are unit vector along x, y, and z. Now f is defined by 2x plus 3zi minus xz plus y j and then y square plus 2zk. Y square plus 2zk, where I, j, k are again unit vector along x, y, z. Y square plus 2z. So let us multiply. So I dot I is 1, j dot j is 1, k dot k is 1, and remaining products are will be 0. So obviously we have del upon del x of 2x plus 3z plus del upon del y minus xz minus y plus del upon del z y square plus 2z. So we are having partial derivative of 2x plus 3z with respect to x will be obviously 2. Similarly, for the next derivative del by del y, we are having minus 1. And for the last term, we are having del by del z of y square plus 2z. Then we are having plus 2 dv. So result will be along v, result will be 2 plus 2 4 minus 1 is 3. So it is 3 dv. Now 3 will be constant, and so it will go outside integration, and we have to just find volume of the surface. And the given surface is basically a sphere which center has 3 minus 1 2 and radius is 3. So obviously formula for a sphere will be 3 as it is, and formula will be 4 by 3 pi r cube, where r is the radius and radius is given by 3 pi r cube. Correct. So let us solve this result finally. 3 will be cancelled out, and 4 pi 3 into 3 into 3. So final result will be 4 pi 3 3 is 9, 9 3 is 27, and it is 108 pi. So this is the final result. So we have asked the value of this double integral, and its value is 108 pi. Let us solve one more problem. Our problem is the vector field f equals to x square I plus zj plus yzk is defined over the volume of the cuboid given by 0 to a, then 0 to b, and then z will be 0 to c, enclosing the surface S. Then again we have to evaluate double integral f dot ds under the surface S. So let us solve this problem also. So again, by Gauss divergence theorem, we are having a statement double integral f dot ds will be equals to triple integral or divergence of f dv. So let us put the result. Triple integral along v under the region v. Divergence is obviously I del upon del x plus j del upon del y plus k del upon del z, where I, j, k are unit vector along x, y, z, and f is given by x square I plus zj plus yzk. Correct. So let us solve this problem again. So dot product will be del by del x of x square will be 2x. Del by del y of z will be 0. And del by del z of last term, that is yz, will be y. And finally, we are also having dv, that is dx, dy, and dz. Correct. Along v. So let us solve this problem with the given limits, and limits are given by double integral x varies from 0 to a, and y varies from 0 to b, and z varies from 0 to c, and function is 2x plus y. So first of all, we will integrate along with respect to z, then y, and then finally x. Correct. So if we integrate with respect to z, we will get x varies from 0 to a, y varies from 0 to b, but when we integrate along z, then result will be 2x plus y, 2x plus y, and it is z taking limit z equals to 0 to c. So we are having limit 0 to a, then 0 to b, and 2x plus y, upper limit minus lower limit, that is c minus 0, and since it is constant, so it will go outside the double integral, and we are having dy dx also, dy dx. Let us integrate with respect to y. Then it will be x equals to 0 to a, and for y it will be 2xy plus y square by 2, and limit will be y equals to 0 to d, and last we will integrate with respect to x after putting the limits. Correct. So let us put the limits. We will get c limit x equals to 0 to a, it is upper limit minus lower limit for y, then it will be 2xb. Similarly, here we are having b square by 2. Correct. And finally integrate with respect to x. So b is common, so it is bc, limit 0 to a, it will be 2x plus b by 2. Just integrate with respect to x, then integration of 2x will be with respect to x will be x square by 2 plus b by 2 into x, and then put the limit x equals to 0 to a. So result will be 2 will be cancelled out, and upper limit a square minus 0, lower limit plus b by 2, x will be a minus 0, that is a. Again, a is common, b and c already outside, and this is a plus b by 2. We can also write a b c by 2 2a plus b. So we have asked the value of this double integral, and its value is abc by 2 into 2a plus b. So these are some references. Thank you so much.